Look up at the night sky on a clear evening, and it appears as a vast, velvety darkness punctuated by the brilliant pinpricks of stars. But what if I told you that this familiar view is only a fraction of the true cosmic story? There's an entire hidden universe, one that our eyes alone can never perceive. Imagine shifting your vision into the infrared beyond what's visible, and suddenly the darkness comes alive. A faint, all-pervading glow emerges, bathing everything in a soft, mysterious light. This is the cosmic infrared background, one of astronomy's most profound and elusive puzzles. It's a whisper from the farthest reaches of time and space, a remnant glow that holds secrets about the earliest epochs of our universe, epochs so distant and strange that they challenge everything we think we know about cosmic history. What makes this glow so extraordinary isn't just its omnipresence, but what it represents. This isn't the light of nearby stars or familiar galaxies. It's the accumulated energy from processes that began when the universe was in its infancy. We're talking about an era just after the Big Bang, when the first stars and galaxies burst into existence, flooding the cosmos with radiation that has been traveling across space for billions of years. The cosmic infrared background is like a fossilized echo of that primeval dawn, and yet it defies easy explanation. Where did this light truly come from? What cosmic engines could produce such a pervasive, uniform glow? Each observation deepens the mystery, hinting at phenomena we're only beginning to grasp: ancient stellar nurseries, supermassive black holes in their youth, or perhaps something even more astonishing waiting to be discovered. This is where our journey begins. Over the course of this video, we'll explore the 25 deepest mysteries of the cosmic infrared background, from its baffling origins to the cutting-edge missions striving to decode its signals. You'll discover how this faint infrared light connects to the formation of the first galaxies, the evolution of dark matter, and even the ultimate fate of the cosmos itself. This isn't just a story about telescopes and data. It's a human story of curiosity, perseverance, and the relentless drive to understand our place in the universe. So come with me as we step beyond the visible into the hidden light that holds the keys to cosmic history. What we find may forever change how we see the night sky and our own existence within it. To uncover this profound discrepancy, astronomers turn to some of the most powerful observatories ever built. The Spitzer Space Telescope, with its infrared eyes, began to map the sky with unprecedented sensitivity. It was soon joined by the Herschel Space Observatory, a colossal instrument with a mirror 3.5 meters across, designed specifically to see the farthest, faintest infrared light. What these two engineering marvels found was not just a little extra light, it was a staggering surplus. When they added up the infrared glow from every known galaxy, star, and cosmic object they could identify, the math fell desperately short. The total background glow was significantly brighter, meaning there were immense sources of light completely missing from our cosmic senses. This wasn't a minor accounting error. It was like counting every single light bulb in a massive city at night and still discovering that the city's glow is twice as bright as all those bulbs combined. Something fundamental was hidden in the darkness. So what could be producing this incredible excess of energy? Scientists were faced with two equally thrilling possibilities, each revolutionary in its own way. The first theory points to a lost generation of galaxies, ones that formed in the universe's chaotic infancy. We're talking about populations of primordial galaxies that are so incredibly ancient, vast, and dust-shrouded that their light is too faint and too redshifted for our current telescopes to see individually. In this early epoch, galaxies were likely bursting with frantic star formation, but all that brilliant visible light was immediately absorbed by thick, choking clouds of cosmic dust. That dust would then heat up and re-radiate the energy as the infrared glow we now detect as the background. It's a ghostly signal from countless forgotten islands of stars, their combined output creating this pervasive cosmic fog. The second possibility is even more exotic, an entirely new type of astrophysical phenomenon that standard models don't account for. Could there be processes in the early universe that we haven't even dreamed of yet? Some theorists have speculated about the violent decay of unknown elementary particles from the dawn of time, releasing energy as they vanished. Others wonder if the earliest supermassive black holes were far more prolific and energetic than we believe, their ferocious feeding frenzies flooding the young cosmos with radiation. This mystery forces us to confront the humbling fact that our inventory of the cosmos is still incomplete. We are either missing a colossal number of celestial objects, or we are missing a fundamental chapter in the physics book of the universe. The origin of this excess infrared light is not just a puzzle, it's a direct challenge to our understanding of cosmic evolution, whispering that the story of how our universe grew up is far richer and more complex than we ever imagined. This brings us to our second great mystery, one that takes us even further back in time to the absolute beginning of cosmic structure. The incredible energy signature of the infrared background might be our only window into the lives of the very first stars to ever ignite, celestial objects so ancient and extreme that we have never directly seen one. Astronomers call these mythical giants population 3 stars. To understand why they are so important, we have to picture the universe before any stars existed. It was a dark, simple place filled only with the primordial hydrogen and helium forged in the Big Bang. There were no heavy elements, no carbon, no oxygen, no iron. Without these heavier atoms, there was no dust, and without dust, the process of star formation had to be completely different. Gravity acted on perfectly pure clouds of gas, allowing them to collapse into behemoths. We're not talking about stars like our Sun. Population 3 stars were monsters, thought to be hundreds of times more massive, burning at ferocious temperatures and living lives that were spectacularly brief. They would have shone with a brilliant, blistering blue-white light, only to explode in colossal supernova after just a few million years, seeding the barren cosmos with the first heavy elements that would later form planets and ultimately us. And this is the heartbreaking problem for astronomers. Their direct light is perpetually out of reach. The universe has expanded so much since that primordial era that the ultraviolet light these stars emitted has been stretched or redshifted far into the infrared part of the spectrum. Furthermore, that faint signal is buried within the overwhelming glow of the cosmic infrared background itself. It's like trying to hear a single voice in a massive choir from miles away. The individual singer is lost in the collective sound. We cannot point our most powerful telescopes at a specific population 3 star. They are all long gone, their lives over in a cosmic instant. This is why the diffuse glow of the CIB is such a tantalizing treasure trove. We may not see them individually, but the combined energy output from the entire population of these first stars would have left an indelible mark on the fabric of the cosmos. Their collective radiation would have helped heat the early universe and contributed to the process of reionization, stripping electrons from atoms and making space transparent to light. That historical event is imprinted on the infrared background. By meticulously dissecting the exact spectrum and pattern of this faint glow, scientists are hunting for a specific signature, a subtle bump or feature in the data that can only be explained by the unique light output of these gigantic, pristine stars. Finding that signature would be one of the most profound discoveries in all of science. It would confirm the existence of our cosmic ancestors, the very first engines that began the transformation of a simple, dark universe into the complex and luminous one we inhabit today. The hunt for population 3 stars within the infrared background is a perfect example of detective work on a cosmic scale, where we must infer the existence of giants from the faintest of whispers they left behind. But if those first stars were the pioneers, the next generation of galaxies were the industrialists, and they presented astronomers with a puzzle just as baffling. We've long imagined the early universe as a pristine, elemental place, a cosmic blank slate. So when our most powerful telescopes like the James Webb Space Telescope began to peer back to within the first billion years after the Big Bang, they expected to see relatively simple, dust-free galaxies. The prevailing thought was that it would take many generations of stars living and dying to manufacture enough heavy elements and spread them widely enough to form significant amounts of cosmic dust. What they found instead was a scene of shocking maturity. Galaxies at cosmic dawn were already incredibly dusty, their visible light choked and transformed into a deep infrared glow. This discovery wasn't just surprising, it overturned our entire timeline for how quickly the universe could become complex. Dust, in the astronomical sense, isn't the stuff you find under your bed. It's a mist of tiny, solid particles, silicates, and carbon compounds that form in the cooling outer atmospheres of aging stars and are then blasted into space when those stars die in supernova explosions. This stardust is the essential ingredient for future planets and even life itself, but the process of making it was thought to be a slow, gradual build-up. To find galaxies already filled with dust when the universe was only 5% of its current age means this enrichment happened at a breakneck, almost impossible speed. It forces us to reconsider the very life cycles of the earliest stars. Perhaps that first generation of population 3 stars didn't just fade away. They might have died in extraordinarily productive supernovae that were far more efficient at forging and dispersing heavy elements than any star death we see today. These hypernova or pair instability supernova could have been the universe's first and most prolific dust factories, operating on an industrial scale almost immediately. The presence of this dust completely changes how we see these infant galaxies. Without it, their brilliant young stars would be clearly visible to our telescopes in ultraviolet and optical light. But the dust acts like a thick cosmic fog, absorbing that fierce starlight. The dust grains heat up, sometimes to temperatures of tens of degrees above absolute zero, and then re-radiate all that captured energy at longer infrared wavelengths. This is a primary source of the diffuse cosmic infrared background. We detect the collective warmth of countless trillions of dust grains, heated by starlight across the cosmos. So these dusty dawn galaxies are not just curiosities, they are major contributors to one of the universe's biggest mysteries. Their hidden light, rerouted into the infrared, is a huge part of the excess glow that our telescopes measure. This revelation creates a fascinating chicken and egg problem for cosmologists. Did the dust form quickly because the first stars were fundamentally different from anything we know? Or were the conditions in these early galaxies uniquely suited to rapid dust production, perhaps with denser gas clouds that could cool and collapse more efficiently thanks to the very dust grains themselves? Each new observation pushes the timeline for dust formation further back, demanding a radical rewrite of our models of galactic evolution. The early universe, it seems, was not a slow and patient place. It was a frenetic, violent workshop, building complexity at a pace we are only beginning to comprehend. Yet the sheer scale of the infrared background suggests this faint glow comes from a staggering number of sources, far more than the few dozen satellite galaxies we see around our own Milky Way. The math points to a universe that should be absolutely teeming with these small, faint dwarfs. Our most sophisticated supercomputer simulations of cosmic evolution, which model the gravitational influence of dark matter, predict this exact scenario. They show vast halos of dark matter condensing after the Big Bang, with smaller clumps merging to form larger galaxies. These simulations tell us that thousands of these small dark matter clumps should have gathered enough gas to light up as dwarf galaxies, becoming permanent satellites orbiting their larger hosts. But when we look out into the local universe, we find only a tiny fraction of the predicted number. They simply aren't there. This glaring mismatch between what our models predict and what our telescopes see is one of cosmology's most persistent headaches, known as the missing satellites problem. So where did all these galaxies go? The faint signal buried within the cosmic infrared background is forcing us to confront this question head-on. One compelling idea is that the galaxies aren't missing at all, they're just too dark for us to see. Perhaps the first generations of dwarf galaxies were incredibly inefficient at forming stars. Their small size meant they had a weaker gravitational grasp on their gas. A single supernova explosion from one of their first massive stars could have easily blown all the remaining star-forming material clear out into intergalactic space, shutting down star production entirely and leaving behind a barren, dark matter halo with only a few old, faint stars. We would be completely blind to such a dark object with our current technology. Alternatively, these primordial dwarfs might be overwhelmingly composed of that very dark matter, with precious little ordinary matter to ever ignite into visible stars in the first place. They would be ghosts, invisible yet massive, their presence only inferred by their gravitational pull. This leads to another, more radical possibility. What if our understanding of dark matter itself is incomplete? The standard model of cosmology uses what's called cold dark matter, which moves slowly and clumps together easily. This model is brilliant at predicting the large-scale structure of the universe, like the cosmic web of filaments and voids. But its failure to predict the correct number of small galaxies suggests it might break down on smaller scales. Some physicists propose alternative models, such as warm dark matter, where the particles move at much higher speeds. This would prevent dark matter from clumping into as many small, dense halos, effectively erasing the smallest potential galaxies from the cosmic blueprint and bringing the simulations more in line with what we actually observe. The fluctuations in the infrared background could be the key piece of evidence needed to test these wild ideas, offering a way to count the true number of early structures that actually formed. The mystery of the missing satellites is a perfect example of how a single, faint signal can challenge the foundations of cosmic science. It pits our most powerful computer simulations against our most sensitive telescopic observations, and for now, the two refuse to agree. The cosmic infrared background sits at the heart of this conflict, its subtle patterns hinting at a hidden population of cosmic building blocks. Unraveling this puzzle could mean we simply need better telescopes to find these faint dwarfs, or it could force a revolutionary rewrite of the nature of dark matter itself. It's a profound reminder that even in the emptiest reaches of space, what we cannot see still defines everything. Pushing even further into the realm of the speculative, our fifth mystery confronts one of the most tantalizing and controversial ideas in all of cosmology: the potential existence of a vast, hidden population of primordial black holes. This hypothesis proposes that the anomalies within the cosmic infrared background might not be from galaxies or stars at all, but from countless black holes that formed not from dying stars, but in the incredibly dense, fractured moments following the Big Bang itself. If true, it would be a discovery that could solve several of the universe's greatest riddles in one breathtaking sweep. To understand why this idea is so revolutionary, we need to distinguish these objects from the black holes we know. The black holes we've detected through gravitational waves or by seeing stars orbit an invisible point are stellar mass black holes. They are the end result of a massive star's life collapsing in on itself after it exhausts its nuclear fuel. Primordial black holes are something else entirely. Theorists propose they could have been forged in the first second of the universe's existence, when space was not smooth and uniform, but a seething, turbulent froth. In certain patches, density fluctuations could have been so extreme that matter collapsed directly into black holes with a wide range of possible masses. Some might be as small as an asteroid, while others could be thousands of times more massive than our Sun. For decades, they have remained entirely hypothetical, a clever mathematical possibility with no concrete evidence to support them. This is where the cosmic infrared background re-enters the story. How could a black hole, an object famous for sucking in light, possibly contribute to a background glow of light? The answer lies not with the black holes themselves, but with the material around them. A primordial black hole wandering through the early universe would be a gravitational trap. It would pull in the primordial hydrogen and helium gas that filled the cosmos along with any dark matter particles. This material wouldn't just fall straight in. It would form a swirling, hot, incredibly dense accretion disk around the event horizon. Friction within this superheated disk would cause it to blaze with intense radiation, potentially outshining entire stars. Now imagine not one, but trillions of these primordial black holes, each acting as a tiny, powerful engine, converting gravitational energy into light across the cosmos. The combined infrared output from all these engines could theoretically contribute to the very background glow we struggle to explain. The implications of this are staggering. For one, it could provide an elegant solution to the mystery of dark matter. What if dark matter isn't a cloud of exotic, unknown particles? What if it's simply this vast number of primordial black holes? They don't emit light, they have mass, and they would gravitationally clump exactly the way our models require dark matter to behave. Their collective infrared radiation could then be a side effect of their dark matter nature. Furthermore, these objects could also be the elusive seeds for the supermassive black holes that now reside at the centers of nearly every large galaxy. We still don't know how these monsters, weighing billions of suns, grew so big so quickly. A population of hefty primordial black holes would provide them with a ready-made head start, a large seed already in place to begin consuming gas and growing from the universe's very first moments. Of course, this remains a highly contested idea. The search for proof is incredibly difficult. Astronomers have looked for the telltale signs of a primordial black hole passing in front of a distant star, an event called microlensing that would briefly magnify the star's light. So far, these searches have largely ruled out the possibility that primordial black holes make up all of dark matter, but they haven't ruled out a significant population with certain mass ranges. The unique, large-scale pattern they would imprint on the infrared background is a different kind of fingerprint, one that new space telescopes and advanced data analysis techniques are now hunting for. Finding their signature woven into the cosmic infrared glow would be one of the most profound discoveries in human history, forcing us to rewrite not only the story of the universe's infancy, but the very nature of the majority of its substance. It's a cosmic high-stakes gamble where the prize is nothing less than a unified answer to several of reality's deepest secrets. Now, imagine the universe as a newborn, just 400,000 years after the Big Bang. It has cooled from a seething plasma into a vast, dark, and silent fog of neutral hydrogen gas. For hundreds of millions of years, this cosmic dark age persists a quiet, simple expanse where no stars yet shine. Then a transformation begins, one of the most critical and poorly understood chapters in all of cosmic history, the epoch of reionization. This was the moment the universe turned the lights on for good, and the faint, all-sky glow of the cosmic infrared background is one of our only windows into how it actually happened. The process itself sounds straightforward. The first stars and galaxies ignite, flooding the cosmos with intense ultraviolet light. This energetic radiation has the power to strip electrons away from the neutral hydrogen atoms that fill all of space, reionizing the gas and tearing apart the primordial fog. Think of it like a colossal sunrise slowly burning away a morning mist across the entire universe. Once this reionization is complete, the cosmos becomes transparent to ultraviolet light, and the age of galaxies truly begins. We know it happened. The light from the most distant quasars proves the fog was cleared by the time the universe was about 1 billion years old. But the how, the when, and the what that caused it remain deeply mysterious. Was it a swift and violent transition or a slow and gradual process? Did brilliant, massive stars do most of the work, or were the feeding supermassive black holes at the heart of young galaxies the primary engines? This is where the diffuse light of the CIB becomes a vital clue. The same sources that produced the infrared background, those first stars and galaxies, are the very objects responsible for providing the photons that drove reionization. Their ultraviolet light did the ionizing, but remember, much of that light was then absorbed by dust and re-radiated as the infrared glow we detect today. By carefully studying the intensity and the pattern of the CIB, astronomers can work backwards. They can estimate the total number of photons these early objects produced, which gives them a crucial constraint on the power available to rip apart the hydrogen fog. It's a complex cosmic accounting problem. To fully reionize the universe, you need a certain number of energetic ultraviolet photons for every hydrogen atom. If the infrared background tells us that the early universe was absolutely teeming with incredibly dusty, star-forming galaxies, then that suggests there was a colossal amount of ultraviolet light being produced, more than enough to get the job done quickly. However, there's a catch. Much of that potent UV light was trapped inside those same dusty galaxies, absorbed before it could ever escape to travel intergalactic distances and ionize the vast neutral reservoirs between galaxies. This creates a fascinating paradox. The most obvious and powerful sources of light might have been ironically inefficient at the specific task of reionization because they were too good at making dust. This dilemma forces scientists to consider alternative contributors. Perhaps the real heroes of reionization were not the giant, dusty galaxies, but a vast population of tiny, faint, and less dusty dwarf galaxies. These smaller systems, which are incredibly difficult to detect even with our best telescopes, might have allowed a much higher fraction of their ultraviolet light to escape directly into space without being absorbed by internal dust. While each one was feeble, their overwhelming numbers could have provided a steady, pervasive drizzle of ionizing photons that slowly but surely cleared the cosmic fog. The pattern of the infrared background's fluctuations could hold the key to distinguishing between these scenarios, hinting at the relative importance of a few brilliant giants versus countless faint dwarfs in lighting up the cosmos. Pinpointing the exact timeline of reionization is another profound challenge. Did it start early and drag on for hundreds of millions of years, or was it a rapid, explosive event? The CIB helps here too, because this light has been traveling for so long. It carries an integrated record of star formation across cosmic time. By measuring the background's spectral energy distribution, essentially its color researchers can gather clues about the era when star formation was at its peak, which should correlate with the peak of ionizing photon production. Current data suggests reionization was likely a drawn-out and complex process, not a single instantaneous event. It may have begun in isolated bubbles around the first clusters of galaxies, which gradually grew and merged until the entire universe was transparent. Unraveling the reionization enigma is about more than just filling in a blank spot in our history books. It's about understanding the conditions that made our modern universe possible. That transition from a neutral to an ionized state set the stage for everything that followed, governing how galaxies could grow and interact. The cosmic infrared background, that faint whisper of warmth from the dawn of time, is one of our most powerful tools for listening to that story. It doesn't give us a simple answer, but it provides the crucial boundaries within which the true, messy, and magnificent narrative of cosmic dawn must have unfolded. If you could view the entire cosmic infrared background not as a uniform sheet of light, but as a dynamic, high-resolution map, you would notice something deeply strange. It's not perfectly smooth. Like static on an old television screen, it's filled with subtle patterns, faint clumps, and intricate fluctuations. This unevenness is what astronomers call anisotropy, and it's here, in these mysterious wrinkles in the fabric of the infrared sky, that we encounter our seventh great mystery. These patterns are a ghostly imprint of the largest structures in the young universe, but they contain twists and turns that our current models of cosmic evolution simply cannot explain. To understand why this is so puzzling, we need to think about how structure formed after the Big Bang. The leading theory tells us that the universe started with tiny quantum fluctuations, microscopic ripples in the density of matter and energy. Over billions of years, gravity amplified these ripples, pulling matter into vast webs and filaments, creating a cosmic architecture often called the cosmic web. At the intersections of these filaments, we find the great clusters of galaxies, while the voids between them are nearly empty. Our powerful telescopes have largely confirmed this picture on scales we can easily observe. So, when we look at the patterns in the cosmic infrared background, we expect its fluctuations to trace this same familiar cosmic web, echoing the distribution of galaxies we see today. But that's not what the data shows. When astronomers meticulously subtract the known contribution from all identified galaxies, a residual signal remains. There are significant anisotropies, clumps of infrared light, that do not correlate with any known large-scale structure. It's as if you were listening to a symphony and could clearly identify every instrument, yet still heard a haunting, melodic hum that wasn't coming from any player on the stage. This leftover signal is real, it's measurable, and it points to a source of light that is either completely invisible to our telescopes or originates from a physical process we haven't yet considered. One compelling explanation is that we are seeing the collective light from a truly primordial population of structures. Imagine the universe's very first galaxies, but not as the relatively bright objects we sometimes glimpse at cosmic dawn. Instead, picture a vast sea of incredibly faint, ultra-low-mass protogalaxies. These would be the smallest building blocks of the cosmic web, so dim and numerous that they blur together into an unresolved fog. Their combined infrared output, the collective warmth of their earliest stars, would create a subtle, large-scale pattern of fluctuations that is fundamentally different from the pattern made by the brighter, later-generation galaxies we can easily catalog. This would be the ultimate signature of the cosmic dark ages giving way to first light, a fossilized imprint of structure formation in its most humble beginnings. Yet there exists an even more exotic possibility. What if these anomalous fluctuations aren't from structures at all, but are instead a signature of entirely new physics operating in the early universe? The intergalactic medium during the first billion years was a bizarre place dominated by dark matter and pristine hydrogen gas. Could there have been processes there that we no longer see today? Some theorists have proposed mechanisms involving the decay or annihilation of dark matter particles. If certain types of dark matter particles can interact with each other or break down, they could release energy in the form of light. This would not be starlight, but something entirely new, a form of radiation generated by the very substance that makes up most of the universe's mass. This dark light would be spread throughout the cosmos, potentially creating its own unique pattern of fluctuations within the infrared background. Another tantalizing idea involves the first supermassive black holes. Their growth is thought to be incredibly messy and violent, potentially shooting out vast jets of energy and matter. The interaction of these jets with the surrounding intergalactic gas could have heated it unevenly, creating enormous bubble-like structures that glow in the infrared. These bubbles would be far larger than any single galaxy, and their faint, diffuse emission could contribute to the anomalous patterns we detect. We're essentially looking for the faint, cooled ashes of the universe's most powerful and ancient explosions. Deciphering this mystery is a monumental task of cosmic cartography. It requires exquisitely sensitive all-sky maps from telescopes like the Spitzer Space Telescope and future missions, combined with sophisticated statistical analysis to separate the known from the unknown. Each anomalous clump is a clue, a whisper from an era when the rules of the universe might have been slightly different. By studying their size, their distribution, and their intensity, cosmologists hope to distinguish between these competing theories. Are we mapping the faintest galaxies in existence, or are we reading the first direct evidence of dark matter's hidden nature? The answer is written in the static of the infrared sky, waiting for us to learn how to read it. This revision of cosmic history is more than just an academic adjustment. It fundamentally changes our perception of the universe's tempo. For a long time, the prevailing narrative was one of a gradual, steady climb, a slow simmer of star birth that reached its peak when the universe was already middle-aged. We pictured a cosmos that took its time, allowing galaxies to mature and accumulate gas over billions of years before hitting their stellar stride. The evidence from the infrared background shatters this leisurely timeline, painting a portrait of an incredibly dynamic and almost frantic adolescent universe. It suggests that the most intense, explosive period of construction happened right out of the gate, in the first few billion years after the Big Bang, an era we now call cosmic noon. This wasn't a slow simmer, it was a brilliant, universe-wide flash in the pan of incredible productivity. To grasp the scale of this shift, we need to understand how astronomers traditionally measured the cosmic star formation rate. For decades, they relied on censuses of galaxies we could directly see, primarily by detecting their ultraviolet light. This method makes intuitive sense. Hot, young, massive stars blaze with intense UV radiation, so the amount of UV light a galaxy emits should be a direct proxy for how many new stars it's forging. This approach worked reasonably well for mapping the more recent, nearby universe, but it contains a critical blind spot, one that becomes a gaping chasm when we look back to the earliest epochs. That blind spot is cosmic dust. In those first galaxies, the very act of rapid star formation created immense amounts of dust. As we've discussed, those massive stars lived fast and died young in spectacular supernova, seeding their surroundings with heavy elements that condensed into tiny solid particles. This dust is incredibly effective at absorbing a galaxy's UV light. It acts like a thick cosmic smog, trapping the brilliant glow of newborn stars and preventing it from escaping. A galaxy could be a furious stellar nursery, but if it's shrouded in dust, it will appear faint or even completely invisible to our UV telescopes. This means our traditional census wasn't just slightly off. It was systematically missing the most active, important star-forming factories in the entire early universe. We were only counting the galaxies that were clean and dust-free, completely missing the dusty powerhouses that were doing the majority of the work. This is the unparalleled value of the cosmic infrared background. It doesn't just see through the dust, it actually sees the dust itself. When that trapped UV starlight is absorbed by dust grains, they heat up and re-radiate the energy at longer infrared wavelengths. The CIB is the sum total of all that re-radiated energy, a direct measurement of all the light that was ever absorbed by dust throughout cosmic history. It's a complete record of star formation that includes both the visible and the hidden galaxies. By carefully measuring the total energy in this background glow and working backwards through models, astronomers can calculate the true total rate at which stars were being born at any given time in the past. The results were staggering. The revised history shows that the universe's star-forming heyday, its cosmic noon, occurred much earlier than we thought, likely within the first 3 to 4 billion years. The peak rate of star birth was also significantly higher, perhaps double or more previous estimates. This forces us to completely reconsider the life cycles of early galaxies. They weren't just slightly more active, they were gravitational engines of unbelievable efficiency, converting gargantuan reservoirs of primordial gas into stars at a ferocious pace that modern galaxies simply cannot match. The early universe was a place of extreme and violent creation, a golden age of galaxy building that we are only now beginning to appreciate thanks to the infrared light that has finally reached us across the gulf of time. But what if the answer isn't hidden in the light of stars at all? This leads us to one of the most electrifying possibilities in modern cosmology, that the anomalous features within the cosmic infrared background could be our first indirect glimpse into the true nature of dark matter itself. The idea rests on a profound and elegant hypothesis that the mysterious substance making up most of the universe's mass might, under the right conditions, literally annihilate itself, transforming directly into detectable energy, including the very infrared light we're trying to explain. To appreciate how radical this is, we need to revisit what we know about dark matter. We are certain it exists because we can see its overwhelming gravitational influence. It holds galaxies together, dictates the motion of galaxy clusters, and forms the invisible scaffolding upon which the entire cosmic web is built. But for all its obvious power, we have no idea what it's made of. It doesn't emit, absorb, or reflect light of any kind, which is why it's called dark. For decades, physicists have proposed candidates for what these invisible particles could be, with one leading favorite being a class of particles known as WIMP, weakly interacting massive particles. The weakly interacting part is key. It means they barely touch normal matter, passing through our planet and our bodies by the trillions every second without a trace. But the annihilating part is where the infrared connection gets fascinating. The theory suggests that when two WIMP particles collide under the right conditions, they could obliterate each other in a tiny, explosive event. According to Einstein's famous equation, their mass would be converted directly into pure energy, typically in the form of other, lighter particles like electrons, protons, or, most importantly for our story, photons of light, including gamma rays and infrared radiation. Now, imagine this not as a rare occurrence, but as a process happening continuously throughout the universe. The highest density of dark matter is predicted to be in the dense centers of galaxies and, even more intriguingly, in the very smallest, earliest dark matter halos that formed after the Big Bang. These primordial clumps would be vast, diffuse spheres of pure dark matter, acting as natural reactors where annihilation could occur at a significant rate. The combined infrared glow from trillions upon trillions of these annihilating dark matter clumps, spread across the cosmos, could theoretically contribute a unique and identifiable signal to the overall cosmic infrared background. The challenge, of course, is finding that signal. It would be like trying to hear a single, specific instrument's note in a symphony orchestra playing at full volume. Astronomers hunting for this signature aren't just looking for extra infrared light. They are searching for a very specific pattern in that light. They create incredibly detailed models predicting what the infrared sky should look like from all known astrophysical sources, distant galaxies, dusty star formation, everything we've discussed so far. Then they compare that model to the actual, all-sky maps from telescopes like Spitzer. The goal is to find a discrepancy, an excess of infrared emission that has the right spatial distribution and spectral signature to match what we'd expect from dark matter annihilation. This expected signature has two key components. First is its distribution on the sky. The signal from annihilating dark matter should be exceptionally smooth and extended, not clumpy like light from individual galaxies. This is because dark matter is thought to form an enormous spherical halo around entire galaxies, including our own Milky Way. An annihilation signal would appear as a faint, large-scale glow centered on our galactic core, diffusing outward into the halo. The second component is its spectrum, its specific color or wavelength. The energy of the photons produced by annihilation depends directly on the mass of the dark matter particle. Different theoretical particles would produce infrared light of different characteristic energies. So, by meticulously analyzing the spectrum of the unexplained parts of the CIB, physicists can essentially test for the presence of specific dark matter candidates, narrowing down their possible mass and properties. This search is a perfect example of high-stakes, needle-in-a-haystack science. Positive claims have been made over the years, with some analyses suggesting that an unexplained, smooth infrared glow from the center of our galaxy aligns perfectly with predictions for certain dark matter particles. However, these claims remain hotly contested. Astrophysicists must exercise extreme caution, as there are many mundane astronomical phenomena that could mimic such a signal. For instance, a population of faint, undiscovered stars like brown dwarfs or rogue planets scattered throughout the galactic halo could produce a similar diffuse glow. Or it could be an unknown aspect of how dust scatters and emits light in our own galaxy. Teasing apart these possibilities requires ever more precise data and increasingly sophisticated statistical tools. The implications of a confirmed detection are almost beyond comprehension. It would arguably be one of the most significant scientific discoveries in history, finally cracking open the 85% of the universe that has remained a complete mystery since its existence was first inferred. It would provide a direct window into physics far beyond the standard model, potentially revealing a whole new sector of particles and forces that operated only in the universe's earliest, most extreme moments. The faint, enigmatic whisper of the cosmic infrared background might just be carrying the first message from that hidden realm, a signal from the dark heart of the cosmos that we are only now learning how to decode. Even as we push the boundaries of observation with marvels like the James Webb Space Telescope, a stubborn and fascinating problem remains. We can now see further back in time than ever before, identifying individual galaxies from the cosmic dawn. Yet, when we add up the light from every single galaxy we've catalogued across the universe, the sum still falls short of the total infrared background glow. This persistent deficit points to a thrilling and humbling possibility that our cosmic inventory is still missing entire populations of galaxies. These aren't just a few faint objects hiding in the shadows. We're likely talking about a vast, hidden cosmos of infrared galaxies that operate by rules we don't yet understand and don't fit neatly into our existing classification systems. Our current taxonomy of galaxies is largely built on what we can see with our own eyes, augmented by telescopes. We have spirals like our Milky Way with their elegant arms. We have ellipticals, giant balls of old stars, and we have irregulars, the chaotic results of galactic collisions. But this entire system is based on the visible light these structures emit, the light that escapes their boundaries and travels across the universe to reach our instruments. What if a significant fraction of galaxies don't play by these rules? What if their most important activity is hidden behind such thick, continuous veils of dust that their visible light is completely suppressed, leaving only a powerful infrared signature as their calling card? This isn't a minor adjustment to our charts. It suggests our fundamental way of categorizing the contents of the universe might be based on a biased, incomplete sample. We've been trying to understand the ocean's ecosystem by only studying the fish that swim near the surface, completely unaware of the bizarre and prolific life forms thriving in the lightless depths below. Deep infrared surveys are the nets we're casting into these depths, and what they're pulling up is baffling. These missions scan the same patch of sky for days, even weeks, accumulating the faintest whispers of infrared light. They repeatedly find sources that are clearly real, significant contributors to the background glow, but which are complete enigmas. Some are incredibly bright in the infrared, yet emit virtually no visible or ultraviolet light, making them impossible to classify with traditional methods. Others have strange, distorted shapes that don't correspond to any known galaxy type, suggesting they are caught in a unique and brief phase of their evolution, one we've never witnessed before. Perhaps they are galaxies undergoing such extreme, buried starbursts that their entire structure is being reshaped from within by the ferocious energy of newborn stars. Or maybe they are the sites of incredibly feeding supermassive black holes, so shrouded in gas and dust that their brilliant accretion disks are completely invisible, with only the warm glow of their dusty donuts revealing their existence. The existence of these unknown populations forces a radical rethink of galaxy evolution. Our models are built on the galaxies we can see, but if a huge number of galaxies spend a large portion of their lives in an obscured, infrared-only state, then we are missing a critical chapter of their life story. It's like trying to understand a human life by only observing adulthood, completely missing the transformative and messy phases of childhood and adolescence. This infrared phase might be the most important period for a galaxy's growth, when it is actively building its stellar population and central black hole. By only studying them before or after this phase, we're seeing the before and after pictures without understanding the dramatic transformation that happened in between. This hidden phase could be the key to solving long-standing puzzles, like how supermassive black holes grew so large so quickly, and how the first galaxies assembled their mass with such astonishing speed. The quest to identify these ghostly infrared galaxies is one of the most active frontiers in astronomy. The strategy involves more than just taking deeper pictures. It requires a multi-wavelength crusade. Astronomers take the coordinates of these mysterious infrared blobs and then point every other telescope they can at them: radio observatories, X-ray telescopes, and of course the mighty Webb. The goal is to get any other shred of data, any alternate view of the object that might reveal its true nature. Sometimes this cross-examination works, and a bizarre infrared source is revealed to be a known type of galaxy, just viewed at an extreme angle or distance. But often, the mystery only deepens. The object remains silent at other wavelengths, a defiantly infrared-only phenomenon. Each one of these stubborn enigmas is a potential flag planted on uncharted territory, marking the existence of a class of celestial object that our textbooks have no name for. They are the cosmic equivalents of the platypus or the coelacanth, living relics that defied all existing categories and forced an expansion of our understanding of life on Earth. The hidden galaxies within the infrared background are doing the same for our understanding of the cosmos, whispering that the universe is far stranger, more diverse, and more inventive than we have yet dared to imagine. Imagine trying to listen for a whisper in a crowded, noisy room. Now scale that up to a cosmic level, and you have the monumental challenge astronomers face when studying the cosmic infrared background. The faint, ancient glow they're trying to measure is incredibly subtle, and it's superimposed on a foreground of local interference that is, ironically, also made of dust. This is the SPHEREx problem, a persistent and deceptive form of contamination that comes from within our own Milky Way galaxy, and it has sparked heated debates for decades about what the true background signal really is. The term SPHEREx here is a beautiful and apt metaphor. Just as wispy, high-altitude ice clouds can obscure our view of the stars on a hazy night, so too does a diffuse fog of cold dust permeate the vast spaces between the stars in our galaxy. This interstellar cirrus isn't made of water ice, of course, but of tiny silicate and carbon-based grains, the same material that makes up the dust in early galaxies. This local dust is cold, often only tens of degrees above absolute zero, which means it naturally glows in the far infrared part of the spectrum, the exact same region where we're trying to detect the most ancient cosmological signals. The problem isn't that this cirrus is bright, it's that it's everywhere. It forms a faint, intricate web of filamentary structures draped across the entire sky, a veiled curtain hanging between our telescopes and the distant universe. Separating this local curtain from the distant cosmic backdrop is a painstaking and imperfect science. It requires building incredibly detailed models of our own galaxy's dust emission. Astronomers use data from missions like Planck and ERAS to map the temperature, density, and distribution of this cirrus across every patch of sky. They then create a foreground template, a predicted map of this local infrared noise, and subtract it from the total all-sky infrared maps produced by telescopes like Spitzer and Herschel. In principle, what should remain is the pure, uncontaminated light of the cosmic infrared background, but in practice the process is fraught with uncertainty. The models are based on assumptions about the composition and behavior of galactic dust that might not be entirely correct. If the model is even slightly off, the subtraction will either leave behind a false residual signal or, just as problematically, subtract out some of the genuine cosmological background along with the cirrus. This uncertainty is the root of the ongoing debate. Different research teams, using slightly different methods and assumptions to model and subtract the galactic foreground, can arrive at starkly different conclusions about the intensity and the pattern of the remaining infrared background. One group might process the data and find a significant, large-scale anisotropy clumpiness that they attribute to the first galaxies. Another group, using a different dust model, might process the same raw data and find the background to be much smoother and fainter, arguing that the first group's result is actually just an artifact of imperfect foreground subtraction. They're not arguing about the data itself, but about the interpretation of the noise. It's a classic case of not being able to see the forest for the trees, except in this case, the trees are the dust clouds of our own galactic neighborhood, and the forest is the entire history of cosmic structure formation. The implications of getting this wrong are enormous. If we overestimate the foreground cirrus, we would underestimate the true cosmic infrared background. This could lead us to think there were fewer early stars and galaxies than there actually were, forcing us to concoct exotic explanations for the missing light. Conversely, if we underestimate the cirrus and assume too much of the signal is cosmological, we might be fooled into thinking we've discovered evidence for entirely new physics, like annihilating dark matter, when in reality we're just seeing a previously unaccounted for component of local dust emission. The credibility of some of the most exciting claims in modern cosmology hinges on our ability to perfect this subtractive process. It's a sobering reminder that to see the universe at its most grand and ancient, we must first understand our own celestial backyard in exquisite granular detail. The quest to solve the cirrus problem is a fundamental, unglamorous, but absolutely essential piece of the puzzle, ensuring that the whispers we hear are truly from the dawn of time, and not just the echo of dust next door. Yet, even after we account for all these known contributors, a stubborn discrepancy remains in the color of the cosmic glow itself. This brings us to our 12th mystery, a puzzle written not in the intensity of the light but in its very shade. The spectral energy distribution of the cosmic infrared background, that is, its precise color signature across different infrared wavelengths, holds a story that doesn't quite match the one our models are trying to tell. It's as if we've identified every instrument in an orchestra based on the sheet music, but the sound we actually hear has a strange, unfamiliar timbre that hints at a phantom instrument playing just out of sight. To understand why this spectral mismatch is so baffling, we need to think about what creates an object's infrared color in the first place. For a dusty galaxy, the spectrum is primarily determined by the temperature of its dust. Just like a piece of iron glowing red, then orange, then yellow as it gets hotter in a forge, interstellar dust grains emit light across a range of infrared wavelengths that directly corresponds to how warm they are. Cooler dust, perhaps found in the quiet outskirts of a galaxy, glows predominantly in the far infrared. Hotter dust, heated by intense starbursts or a voracious black hole near the galaxy's core, radiates more of its energy at shorter, mid-infrared wavelengths. Our models of galaxy evolution make very specific predictions about how much of each type of dust should exist in the early universe, and therefore what the combined color of all their light should be. When we compare these predictions to the actual, measured spectrum of the CIB, the two curves don't align perfectly. There's an unexplained excess of light at certain wavelengths, particularly in the mid-infrared range. This tells us that the universe seems to have more warm dust than our theories say it should. we're left with two equally compelling possibilities, each forcing a radical rethink of cosmic physics. The first is that our basic assumptions about the dust itself are wrong. The dust grains in early galaxies might have been fundamentally different from the dust we study locally. Perhaps they were made of purer materials or had different sizes and shapes, which would change how efficiently they absorb and re-radiate starlight. A different composition could make dust heat up and glow more efficiently at specific temperatures, explaining the anomalous color signature we detect. It's a reminder that the early universe was a unique laboratory, capable of creating materials under conditions we cannot replicate. The second, far more exotic possibility is that we are seeing the signature of radiation mechanisms that have nothing to do with starlight or dust at all. What if the excess mid-infrared glow isn't from heated solids, but from some form of direct emission? Some theorists have looked to processes like the decay of exotic particles, as we discussed with dark matter, which could release photons at very specific energies. Others wonder if the frenetic environment around the first supermassive black holes produced radiation in ways we don't see in their modern, more settled counterparts. Perhaps immense shocks from galaxy collisions or powerful jets from quasars created widespread conditions for light emission that bypassed the usual dust heating process entirely. These wouldn't be minor adjustments to our models. They would be indications of entirely new chapters in astrophysics, processes that were common in the extreme environment of the young cosmos but which have since faded away. Deciphering this spectral riddle is like being a cosmic forensic scientist, analyzing the light from a crime scene to determine what kind of weapon was used. The unique fingerprint of the light, its intensity at each specific wavelength, is our only clue. Missions like the upcoming SPHEREx observatory are designed specifically for this kind of detective work. By mapping the entire sky in hundreds of precise infrared colors, it will produce a hyper-detailed spectrum of the cosmic background, allowing scientists to identify the exact wavelengths where the discrepancies are strongest. This data could finally allow us to distinguish between the two possibilities. Is the anomalous color the result of weird dust, or is it the first faint signal of a cosmic process we have yet to name? The answer will force us to either revise our understanding of the most basic building blocks of galaxies, or to accept that the early universe operated on a set of physical rules far stranger than we ever imagined. This brings us to a profound and deeply puzzling aspect of the cosmic infrared background, the mystery of its evolution through time. If we could rewind the cosmic clock and watch the CIB develop, we would expect its story to follow the narrative we've constructed from visible light observations. A slow and steady rise in activity leading to a peak of star formation around cosmic noon, followed by a gradual decline to the quieter universe we see today. But the CIB tells a different story, one that unfolds at a different pace and with a different intensity, suggesting that the hidden, dust-obscured universe has its own unique history, operating on a separate timeline from the one written in starlight. The core of this mystery lies in a surprising disconnect. When astronomers measure the CIB's intensity at different redshifts, essentially peering back into different chapters of cosmic history, they find that its strength doesn't perfectly align with the star formation history we've painstakingly mapped from ultraviolet and optical surveys. According to those traditional measurements, the universe's productivity hit its peak when it was around 3 to 4 billion years old. But the integrated energy of the infrared background suggests something far more extreme. It points to an era of truly ferocious hidden activity that may have started even earlier and been significantly more intense than our standard models allow. It's as if we've been reading a biography of a famous figure that only covers their public life, while the infrared data reveals a previously unknown, explosive, and transformative period of their youth that completely recontextualizes their entire story. So what could cause this divergence in timelines? One compelling idea is that the very earliest galaxies were not just slightly dustier, but existed in a perpetually shrouded state. In the first few billion years, the universe was a much denser place. Galaxies were smaller, gas clouds were more compact, and collisions between galaxies were far more frequent. These conditions are a perfect recipe for creating and trapping immense amounts of dust. A galaxy in this era might have spent its entire brilliant, star-forming life almost completely cocooned, its visible light never escaping. Its entire contribution to the cosmic ledger would be in the infrared, and it would be entirely missed by our UV-based sensuses. This means the peak of cosmic star formation wasn't just a period of higher activity. It was an era dominated by a different kind of galaxy, one that was fundamentally obscured and whose life story is only recorded in the infrared background. This leads to another fascinating possibility, that the relationship between a galaxy's stars and its dust changes over cosmic time. In the modern, more spread-out universe, a supernova explosion can blow dust clear out of a galaxy, preventing it from building up thick, continuous shrouds. But in the dense, gravity-rich early universe, galaxies might have been better at holding onto their dust. Their stronger gravitational pull could have trapped the material ejected by dying stars, allowing it to accumulate into permanent, opaque clouds. This means the same physical process, a star-going supernova, would have had a completely different outcome depending on when it happened. In the past, it enriched and obscured its galaxy. In the present, it cleans and exposes it. This evolving feedback loop could be the key to understanding why the hidden universe of the past was so much more prolific and why its history, as written in the CIB, follows its own distinct arc. The implications of this time evolution mystery force a major revision of galaxy evolution models. Our current simulations are incredibly sophisticated, but they are built to reproduce the universe we see. If a significant portion of the universe's energy output throughout history has been hidden from our view, then those models are missing a critical variable. They might accurately simulate the growth of the visible stellar mass in galaxies, but they could be drastically underestimating the total amount of star formation that actually occurred, especially in the critical first few billion years. Getting the timeline right isn't just an academic exercise. It's essential for understanding how galaxies grew their supermassive black holes, how they enriched the cosmos with heavy elements, and ultimately how systems like our own Milky Way came to be. The anomalous evolution of the cosmic infrared background is a powerful clue, telling us that the true story of cosmic dawn was not just brighter, but also darker, dustier, and more dramatic than we ever dreamed. Yet the story doesn't end with a simple comparison of maps. The most profound clues come from measuring the subtle ways these background radiations influence one another across billions of years. A powerful technique called cross-correlation allows scientists to search for these hidden connections. By taking the incredibly detailed map of the cosmic microwave background, particularly its patterns of temperature and polarization, and mathematically comparing it to the map of the cosmic infrared background, astronomers can detect whether the two are linked in ways that defy simple coincidence. Imagine two choirs singing in different languages. Cross-correlation is the process of discovering if their melodies are subtly harmonizing, suggesting a shared conductor or a common musical source. These studies have revealed something extraordinary. The distribution of the ancient infrared light from the first galaxies does indeed show a statistically significant correlation with the primordial seeds imprinted in the microwave background. This isn't just a faint echo, it's a measurable handshake between the universe's birth and its adolescence, confirming that the giant structures we see forming in the CIB truly did grow from those initial quantum fluctuations. But within this confirmed connection lies a deeper puzzle, one that points toward potential new physics. The strength of the correlation observed in some studies appears to be slightly stronger than what our standard model of cosmology predicts. According to our best theories, the gravitational influence of dark matter should be the primary force guiding this relationship, with the distribution of early galaxies, and thus their infrared light naturally tracing the underlying dark matter scaffold that itself grew from the CMB fluctuations. If the observed correlation is anomalously strong, it suggests that this gravitational picture might be incomplete. Perhaps another, non-gravitational process is also at work, one that directly connects the energy of the early universe to the formation of its first light sources. Some theorists have proposed that certain inflationary models, which describe the universe's violent expansion in its first fraction of a second, could produce unique patterns that simultaneously affect both the CMB and the later formation of structures in a more directly linked way than pure gravity allows. Others wonder if dark energy, the mysterious force accelerating the universe's expansion, could have had a different nature or strength in the past, subtly altering how structures grew and how their light now correlates with the ancient past. This large-scale correlation extends beyond the CMB to the distribution of galaxies in the nearby universe. When astronomers cross-correlate the infrared background map with vast optical galaxy surveys that map the cosmic web of our modern era, they again find a connection that is both expected and strangely potent. The infrared glow clumps in a way that aligns with the filaments and nodes of the cosmic web we see today, which makes sense. The ancient galaxies that produced the CIB are the ancestors of the galaxies we see now. However, the infrared light seems to be a more sensitive tracer of the true underlying mass distribution, even highlighting the faint, diffuse strands of the web where very few visible galaxies reside. This suggests the CIB is picking up the collective light from that vast population of missing dwarf galaxies, or even from the intra-halo light stars ripped from galaxies during collisions and now drifting in the dark spaces between them. The infrared background, in this sense, acts as a floodlight, illuminating the full, dark matter Chinese letter of the cosmos in a way that visible light surveys cannot. Ultimately, these large-scale connections transform the cosmic infrared background from a mere fossil into an active diagnostic tool for the universe's architecture. Its correlation with other fundamental markers provides a crucial consistency check for our entire cosmological model. When the connections align with predictions, it builds confidence in our understanding of dark matter and gravity. When they deviate, as they sometimes do, they open thrilling windows into what might be missing from that understanding. These subtle, statistical anomalies are the whispers of unknown processes, perhaps new fields, new particles, or new principles governing the interaction between light and matter on the largest scales. By listening to the harmonious yet occasionally discordant relationship between the universe's oldest light and its first starlight, we are not just reading history, we are stress-testing the very laws of physics across the entirety of cosmic time. This leads us to a fundamental and deeply puzzling question. How did the universe get so dusty so fast? To explain the incredible infrared glow we see from cosmic dawn, the early cosmos must have been absolutely filled with dust. But the traditional timeline for making cosmic dust simply doesn't work on such an accelerated schedule. This is our 15th mystery, the dust production timeline, a puzzle that forces us to consider whether the first stars died in ways fundamentally different from anything we see today. In our modern, well-established universe, dust production is a slow and cyclical process. It starts with aging stars. As sun-like stars reach the end of their lives, they puff off their outer layers in a relatively gentle process, creating beautiful planetary nebulae and seeding space with newly formed dust grains. More massive stars contribute as well, ending their lives in violent supernova explosions that forge heavy elements and blast them outward. But even then, the process isn't perfectly efficient. The tremendous shockwaves from a supernova can actually destroy more dust than it creates in the initial blast, and it takes time for the ejected material to cool, condense, and coalesce into new solid particles. This entire cycle requires multiple generations of stars living and dying to build up the abundant dust we see in mature galaxies. It's a gradual, multi-billion-year recycling program. Now rewind the clock to the universe's first billion years. This is the era we need to explain the dust that shrouded those early galaxies and created the infrared background. According to the gradualist model, there simply shouldn't have been enough time for this process to run even once, let alone multiple times. The most massive stars, the ones that die the quickest, have lifespans of a few million years. That sounds fast, but you then need time for their ejector to travel, cool, and form dust. Then, that dust needs to be incorporated into a new generation of stars. The problem is that the infrared background indicates massive dust masses hundreds of millions of times the mass of our Sun, already in place when the universe was only 5% of its current age. The standard playbook for making dust is too slow by a factor of 10. This glaring timeline problem has led astrophysicists to propose a far more dramatic origin story, that the very first supernova were not just explosions but hyper-efficient, universe-altering dust factories. We're talking about a type of stellar death so extreme that it no longer occurs in the modern universe. The leading candidates are pair instability supernova. These are hypothetical explosions of truly monstrous first stars, those pristine population, three giants that could be 200 or 300 times the mass of our Sun. The physics inside such a behemoth is mind-bending. As it burns through its fuel, the core becomes so hot that light itself spontaneously transforms into matter, electron and positron pairs. This process robs the star of the internal pressure supporting it against its own immense gravity, leading to a catastrophic collapse and a subsequent explosion so powerful that it completely unbinds the star, leaving no black hole behind. Why would this be good for making dust? Because such a violent and complete explosion would eject a staggering volume of newly forged heavy elements, the entire contents of the star's interior, out into the cold surrounding gas in a single titanic event. The conditions in these expanding ejecta could be perfect for rapid dust condensation. Calculations suggest that a single pair instability supernova could produce enough dust to form thousands of Earth-sized planets. If the first generation of stars was dominated by these monsters, they could have flooded the infant cosmos with dust in a single, incredibly productive wave of destruction and creation. It's a breathtaking idea that the universe's first dust, the raw material for future planets and life, was not made in a slow grind, but in a fireworks display of unimaginable scale, a brief era of hyper-violent stellar deaths that set the stage for everything that followed. But is this the only explanation? Some scientists argue that alternative, less dramatic pathways could also bridge the timeline gap. Perhaps dust formation in the early universe was simply more efficient. The environment surrounding the first supernova was different, colder, denser, and made of pure hydrogen and helium. Without any pre-existing seed dust grains to help with cooling, gas clouds might have had a harder time collapsing to form the first stars. But once that first wave of supernova occurred, the first dust grains they produced would have acted as incredible catalysts. These tiny solid particles are brilliant at radiating away heat. Their sudden presence would have allowed gas clouds to cool and collapse into new stars far more rapidly than before, essentially kickstarting a positive feedback loop of star formation and dust production. In this scenario, you don't need each supernova to produce unheard of amounts of dust. You just need the process to become exponentially more efficient once it starts, like a chain reaction, rapidly building up dust masses to the levels we infer. There are even more exotic ideas on the table. Could some dust have formed not in supernova, but in the powerful outflows from the earliest quasars? The accretion disks around supermassive black holes are incredibly energetic environments, driving immense winds of material into space. As this hot gas expands and cools, it might provide another avenue for rapid dust formation. Or what about in the dense, colliding shells of material when the outflows from one supernova crash into the ejecta from another? In the crowded conditions of a primordial star cluster, such collisions might have been common, creating localized regions ideal for turning gas into solids. The answer to the dust timeline mystery is more than just an academic detail. It gets to the very heart of how quickly the universe transitioned from a simple, empty state to a complex, chemically rich one. If pair instability supernova were the primary engine, it paints a picture of a dramatic and terrifyingly violent cosmic dawn over almost as soon as it began. If instead a combination of efficient processes is to blame, it suggests a more nuanced and sustained period of development. The key to distinguishing between these ideas lies in the detailed properties of the dust itself, clues that are encoded in the precise spectral signature of the cosmic infrared background. The wavelength of its glow tells us about the dust's temperature, and the pattern of that glow might eventually reveal the typical size of the grains. The dust from a pair instability supernova might have a different size distribution than dust made in a quasar outflow. By continuing to dissect this fossilized light with ever more powerful telescopes, we are not just studying dust, we are reading the obituaries of the first stars, trying to understand how their spectacular deaths built the foundations for the world we see today. But to truly explain the sheer power behind the cosmic infrared background, we must venture into the hearts of galaxies themselves, to the most energetic engines in the universe. This brings us to our 16th mystery, the potential legions of hidden active galactic nuclei, whose colossal black holes are so shrouded in dust that their furious light is completely transformed, forcing a radical rethink of how these monsters grew and shaped the cosmos from the very beginning. An active galactic nucleus, or AN, is the incredibly bright, compact region at the center of a galaxy where a supermassive black hole is actively feeding. As vast quantities of gas and dust spiral inward, they form a searingly hot accretion disk that can outshine billions of stars. But crucially, our view of this brilliance depends entirely on our angle. If we look directly down onto the accretion disk, we see a brilliant quasar. But if our view is edge-on, we see something entirely different. The black hole and its disk are then surrounded by a thick, dusty torus, a gigantic donut-shaped structure that absorbs the immense ultraviolet and X-ray radiation from the core and re-radiates it as a powerful infrared glow. From our perspective, the dazzling central engine is completely hidden. We only see the warm, dusty echo of its feast. This is an obscured AGN, and it may be the rule, not the exception, especially in the early universe. The profound implication for the cosmic infrared background is that a huge portion of its energy might not be from starlight at all. It could be the collective waste heat from trillions of these hidden black hole banquets, their visible brilliance converted into a pervasive infrared fog. This challenges a fundamental pillar of our understanding. What is the primary power source in young galaxies? We often assume it's starlight, but if obscured AGN are ubiquitous, then the energy output of the early cosmos was significantly influenced by black holes from the very start. This isn't just a minor adjustment. It suggests that black holes and their host galaxies grew up together in a far more intimate and codependent way than our standard models suggest, a relationship hidden from our view until now by colossal veils of dust. This possibility also offers a potential solution to one of the biggest puzzles in black hole science. How did supermassive black holes get so big so fast? We see quasars with billions of times the mass of our Sun already in place when the universe was less than 1 billion years old. Growing such behemoths through accretion takes time and a nearly continuous supply of gas. If a large population of the first galaxies hosted these hidden, feeding black holes, it means the early universe was far more efficient at funneling material into the central engine than we thought. The dust that obscures them isn't just a curtain, it might be a key part of the feeding mechanism itself, helping to cool the inflowing gas and allowing it to fall inward more steadily. The infrared background in this light becomes the thermal signature of the universe's most successful feeding frenzy, a record of black holes growing at a breakneck pace right from the dawn of time. Unraveling this mystery requires a multi-wavelength detective hunt. Astronomers take the coordinates of mysterious infrared sources that contribute to the background and point X-ray telescopes at them. X-rays are powerful tools because they can punch through even thick dust, potentially revealing the hidden heart of an AGN. When they find a strong X-ray source coinciding with a brilliant infrared object, it's a strong sign of a buried black hole. The James Webb Space Telescope is taking this further, using its infrared eyes to study the spectra of these objects. The specific way dust absorbs and re-emits light can leave a unique fingerprint, a signature that betrays the presence of a powerful central engine hidden within. Each confirmed obscured AGN is another piece of the puzzle, helping us estimate what fraction of the infrared background's power comes from hidden black holes versus buried starlight. The answer will reshape our cosmic history. If obscured AGN are the dominant contributor, it means the early universe was a far more violent and chaotic place, with black holes playing a leading role in governing galaxy evolution through their powerful jets and radiation, which can heat gas and shut down star formation. If they are a smaller but significant component, it points to a more balanced co-evolution, where intense starbirth and black hole growth are two sides of the same dusty coin. The faint, all-sky infrared glow is the integrated record of this hidden relationship, a testament to the fact that the most powerful forces in the cosmos often operate not in brilliant visibility, but from behind the deepest veils. Even as we strive to peer into the deepest reaches of the cosmos, one of the most persistent and deceptive sources of interference shines from right here in our own celestial neighborhood. This is the challenge of the zodiacal light, a faint glow caused by sunlight scattering off countless tiny dust particles that fill the plane of our solar system. This cloud of interplanetary dust, the leftover debris from asteroids and comets, forms a luminous band along the ecliptic, and its infrared emission is a formidable contaminant that must be meticulously stripped away to reveal the true extragalactic cosmic infrared background. The process of doing so is one of the most delicate and contentious tasks in modern cosmology, where the line between a profound discovery and a systematic error is vanishingly thin. Subtracting this local glare is a monumental exercise in precision modeling. Astronomers must construct a highly detailed, three-dimensional map of the solar system's dust distribution. They use data from multiple space missions, observing the zodiacal light from different vantage points throughout the year as Earth orbits the Sun. The goal is to understand how the density and temperature of this dust cloud vary with distance from the Sun and position within the solar system. This model is then used to predict exactly how much infrared emission this dust would produce in every single pixel of a telescope's all-sky map. In principle, once this predicted foreground is subtracted, the pristine light of the distant universe should remain. But in practice, the model is built on a series of complex assumptions about the size, composition, and distribution of these dust grains, assumptions that might not be entirely correct. The heart of the ongoing debate lies in the subtle uncertainties of this subtractive process. Different research teams can use slightly different dust models or statistical techniques to handle the zodiacal light, and they can arrive at starkly different conclusions about the intensity and structure of the remaining infrared background. One group might process the data and identify a significant, large-scale anisotropy that they attribute to the clustering of the first galaxies. Another group, using a different approach to zodiacal subtraction, might find the background to be much smoother and fainter, arguing that the first group's detected signal is actually just residual noise from an imperfect model of our own solar system's dust. They're not arguing about the raw data from the telescope, they're arguing about the interpretation of the foreground, a classic case of struggling to see the distant forest because of the dusty trees in our own yard. These residual uncertainties have direct consequences for some of the most exciting claims in extragalactic astronomy. For instance, the credibility of a potential signal from annihilating dark matter or from a population of primordial black holes hinges on our ability to prove that a detected infrared excess is truly cosmological and not just a leftover artifact of local zodiacal contamination. A slight oversubtraction of the solar system's glow could lead us to underestimate the true background, making the early universe seem less active than it truly was. Conversely, an undersubtraction could create a false excess of infrared light, tempting us to invent exotic new physics to explain a signal that simply comes from our own solar system's backyard. This painstaking, unglamorous work of foreground modeling is therefore one of the most critical and foundational steps in the quest to understand the universe's first light, a sobering reminder that to see the farthest horizons, we must first achieve an intimate understanding of our own home. Yet this leads us to a profound and often overlooked limitation in our quest to understand the cosmos, one rooted in a simple but humbling fact. We have only one universe to observe, and we are stuck in a single location within it. This is the problem of cosmic variance, a fundamental source of uncertainty that challenges our ability to ever know the true, average properties of the infrared background. Imagine trying to determine the global climate of Earth by only ever measuring the weather in your own backyard. Some days are sunny, some are rainy, and from your limited data, it's incredibly difficult to say what the planet's overall average temperature truly is. Now scale that up to a cosmic level. Our entire observable universe, for all its vastness, might itself be just a single backyard within a much grander cosmos, and its specific properties may not be perfectly representative of the whole. This variance isn't just a philosophical idea, it has direct, measurable consequences for the cosmic infrared background. When our space telescopes like Spitzer or Herschel map the sky, they don't see a perfectly uniform sheet of light. Instead, they see a tapestry of light and dark patches, regions where the infrared glow is stronger and regions where it is weaker. Some of this pattern is real, the actual clustering of ancient galaxies and the large-scale structure of the universe. But some of it is simply due to our limited perspective. We are looking out from a specific point in space, and the particular arrangement of structures along our specific line of sight is unique. Another observer in a different galaxy making the same measurements would see a slightly different pattern of fluctuations and might therefore calculate a slightly different average intensity for the entire background glow. This means that the very numbers we use to define the CIB, its total brightness, the strength of its fluctuations, are not absolute cosmic constants. They are, to some unknowable degree, influenced by our own place in the universe. The challenge is separating the signal from the sampling error. Astronomers must use sophisticated statistical tools to estimate how much of the pattern they see is genuine information about the early universe and how much is just the cosmic equivalent of sampling noise. For very large scales, approaching the size of the observable universe itself, this variance becomes a dominant source of uncertainty. It means there is a fundamental limit to how precisely we can know the true power of the infrared background or the exact timing of cosmic dawn. No matter how powerful our telescopes become, we can never escape our one fixed vantage point. We are forever decoding the universe from a single, privileged, but ultimately limited seat in the cosmic auditorium. This inherent uncertainty forces a necessary humility into the interpretation of our data. When two different observational teams arrive at slightly different results for the properties of the CIB, it isn't necessarily that one is wrong. They might be studying two different patches of sky, two different backyards of the cosmos, each with its own slightly different history and population of early galaxies. The discrepancy between their results could be a direct measurement of cosmic variance itself, a tangible reminder that our view of the heavens is always and inevitably a local view. Accepting this limitation is not a surrender, it is a crucial part of the scientific process. It teaches us to express our findings not as absolute truths, but as careful estimates with well-defined error bars that acknowledge our lonely, singular perspective within the grand and possibly infinite tapestry of existence. And here we arrive at a profound technical hurdle that lies at the very heart of deciphering the cosmic infrared background, a challenge so fundamental it redefines how we must do science. This is the resolution problem. For all their incredible power, our infrared telescopes like Spitzer and Herschel face a simple, physical limitation. When they stare into the depths of space, the countless distant, faint galaxies that contribute to the background glow are so numerous and so far away that they blur together into an unresolved fog. We are not seeing a sky full of distinct pinpricks of light. We are seeing the blended, collective warmth of a universe of sources, a cosmic puree where the individual ingredients are indistinguishable. This transforms a seemingly straightforward counting exercise into one of the most complex inferential tasks in all of astronomy, a classic inverse problem. An inverse problem is in essence a detective story where you start with the final effect and must work backwards to deduce the cause. It's like trying to determine the size, shape, and number of stones dropped into a pond by only analyzing the complex pattern of ripples that eventually reaches the shore. You know the ripples came from the stones, but you can't see the stones themselves. In the case of the CIB, the ripples are the faint, large-scale fluctuations, the subtle anisotropies in the infrared glow. Those stones are the properties of the hidden galaxy population. Their individual brightness, their average distance, how clustered together they are, and their total number. We are presented with the final, blended signal and must use statistical sorcery to reverse engineer the characteristics of the sources that created it. This forces astronomers to become masters of statistical inference rather than just observers. The primary tool for this is a powerful technique called fluctuation analysis. Here's how it works in practice. Scientists take a deep image from an infrared telescope, a picture that appears as a grainy, textured field of light. The first step is to carefully subtract all the identifiable foreground sources, the nearby stars and galaxies we can actually resolve. What remains should be the smooth, uniform background, but it isn't. It still has a texture, a specific kind of graininess. This graininess isn't random noise, it's the signal. By measuring the statistical properties of this graininess, how clumpy it is, and how the size of those clumps varies across the image, researchers can begin to build a model of the hidden sources. Larger clumps in the background suggest that the unseen galaxies are highly clustered together, tracing the invisible dark matter filaments of the cosmic web. The intensity of the fluctuations gives clues about the average brightness of the individual sources. It's a painstaking process of creating millions of simulated universes on a supercomputer, each with a different set of rules for its galaxy population, and then seeing which simulation, when blended together, produces a pattern of fluctuations that perfectly matches the real data we see from our telescopes. The limitations of our instruments directly dictate what we can learn. A telescope's angular resolution, its ability to distinguish two separate points of light, sets the minimum scale at which we can perform this analysis. If the unseen galaxies are too close together on the sky, smaller than the telescope's resolution limit, they will forever remain blended. This is why the James Webb Space Telescope is such a revolutionary tool. Its giant mirror and exquisite resolution allow it to push this boundary further than ever before. Where Spitzer and Herschel saw only an unresolved glow, Webb is now beginning to resolve a fraction of that fog into individual, faint specks, the very galaxies that were previously just a statistical prediction. Every time Webb successfully resolves what was once a part of the background, it provides a crucial anchor point for the fluctuation models, confirming that the statistical inferences were correct and allowing us to peer even deeper into the remaining unresolved light with greater confidence. This iterative process of prediction followed by partial confirmation is how we slowly unmask the hidden universe, turning statistical probabilities into confirmed cosmic census data. What if the very framework we use to understand the cosmos is slightly but profoundly wrong? This brings us to one of the most radical and mind-bending mysteries surrounding the cosmic infrared background: the possibility that its puzzling features are not caused by hidden galaxies or exotic particles, but are instead the first hints that Einstein's theory of gravity itself needs a revision on the largest scales. For nearly a century, general relativity has been the undisputed foundation of cosmology, perfectly predicting the behavior of planets, the bending of light, and the expansion of the universe. Yet, its potential failure to explain the anomalies in the infrared background forces us to consider that the rules of the universe might be different than we've always assumed. The core of this idea stems from a deep unease with the current cosmological model's reliance on invisible components. To make Einstein's equations work on the scale of the entire universe, we have had to invent two mysterious substances: dark matter to explain how galaxies hold together, and dark energy to explain the accelerating expansion. Together, these two unknown entities make up 95% of the entire cosmos. For many physicists, this is a profoundly unsatisfying situation, a universe where the vast majority of its content is completely unexplained. This has led some researchers to propose a different path. Instead of inventing new forms of matter and energy, perhaps we should modify the theory of gravity itself. These ideas are known as modified Newtonian dynamics, or MND, and its relativistic extensions. So how could a modified theory of gravity explain the cosmic infrared background? It all comes back to the growth of structure. In the Standard Model, the specific pattern of fluctuations we see in the CIB, the size and distribution of its faint clumps, is a direct result of dark matter's gravitational influence pulling matter together over billions of years. If you were to remove dark matter from the equations, the predicted pattern would look completely different. Galaxies wouldn't form quickly enough or cluster in the same way. Proponents of modified gravity argue that their altered equations, which strengthen the force of gravity in specific regimes where it's very weak, could potentially generate that same clustering pattern without the need for any dark matter. The anomalous anisotropies in the infrared background could then be a signature of this alternate gravitational law in action during the universe's formative years. The infrared background becomes a crucial new testing ground in this high-stakes debate. Its light is an integrated record of structure formation from the very first galaxies onward. The precise statistical properties of its fluctuations, the subtle way its glow is textured, encode a history of how matter clumped together under gravity. By comparing these observed textures to the predictions of both the Standard Model and various modified gravity theories, cosmologists can perform a direct test. It's a cosmic fingerprint, and the question is which theory it matches. Some preliminary studies have suggested that the large-scale correlations in the CIB might align slightly better with certain modified gravity predictions, providing a tantalizing, though highly controversial, hint that there might be more to gravity than Einstein conceived. This pursuit is about far more than just a theoretical preference. It strikes at the heart of the scientific method. A successful theory must not only explain what we already see, but also make bold, testable predictions about what we will find. The Standard Model of cosmology, with its dark matter and dark energy, has been incredibly successful at predicting the large-scale structure of the universe and the properties of the cosmic microwave background. For a modified gravity theory to truly compete, it must be able to replicate all of those successes and provide a better explanation for anomalies like the CIB fluctuations. It must be a complete, self-consistent framework, not just a clever fix for a single problem. This is an enormous challenge, and no modified gravity theory has yet cleared this extraordinarily high bar. Whether these anomalies ultimately point to new physics or simply to a more complex understanding of dark matter, their value is undeniable. They push our theories to their breaking points and force us to question our most fundamental assumptions about how the universe works. The cosmic infrared background, that faint whisper of heat from the dawn of time, has become an unexpected arbiter in one of physics' greatest debates, proving that even the most established laws of nature must always stand ready to be tested by the next great observation. But the grand architecture of the universe extends far beyond the bright islands of galaxies. It includes the vast, dark filaments that connect them. This brings us to our 21st mystery, a search for the faintest possible signature woven into the infrared background, the direct glow of the cosmic web itself. We've long known this web exists, a sprawling network of dark matter traced by galaxies, but the idea that its faint strands might actually shine with their own light pushes our observational capabilities to the absolute limit. Finding this signature would be like seeing the ghostly girders of a colossal bridge, whose existence we've only inferred from the traffic moving across it. How could these near-empty voids between galaxies possibly produce light? Theorists have proposed several fascinating mechanisms. The most straightforward involves the sparse gas that does reside in these filaments. While incredibly diffuse, this material isn't completely cold. It can be heated by the intense ultraviolet background radiation that permeates space, a leftover glow from countless quasars and galaxies. This gentle heating could, in theory, cause the gas to emit a faint, extremely extended ultraviolet glow. But due to the expansion of the universe, that light would be redshifted directly into the infrared part of the spectrum by the time it reaches us. We'd be looking for the warmed breath of the cosmos's loneliest places. Another, more dramatic possibility involves shock heating. As gravity pulls matter along the cosmic web into the dense nodes where galaxy clusters form, gas can crash into other streams of gas at velocities of hundreds of kilometers per second. These collisions would create immense, gentle shock waves that travel through the filaments, heating the gas to temperatures of tens of thousands of degrees. This heated gas would then radiate its energy, potentially in the far infrared. It would be the faint, cooling ember of a silent, billion-year-old collision, a testament to the slow-motion violence of cosmic structure formation. Then there's the most exotic candidate, the indirect glow of dark matter. If dark matter particles can annihilate or decay, as we discussed earlier, they would do so everywhere they exist. The highest densities are in the centers of galaxies, but dark matter also forms those massive, diffuse filaments of the cosmic web. While the signal would be incredibly weak in these vast, empty regions, the sheer volume of these filaments means their total contribution could add up to a unique, large-scale pattern of infrared light. This would not be the light of ordinary matter, but a direct map of the dark matter skeleton itself, glowing from within due to its own hidden physics. The monumental challenge, of course, is seeing any of this. The predicted signal is beyond faint. It is buried within the already subtle fluctuations of the cosmic infrared background. Isolating it requires not just sensitivity, but a profound understanding of everything else that contributes to the infrared sky. Astronomers must first subtract the emission from all known galaxies, then the zodiacal light from our solar system, then the cirrus from our galaxy. What remains is a field of extreme noise. The hunt for the cosmic web signature is a search for a specific, statistically significant pattern within that residual noise, a pattern that aligns perfectly with the predicted distribution of the web's filaments from dark matter maps. This is where the cross-correlation techniques we mentioned earlier become absolutely vital. Scientists take a map of the cosmic web structure as inferred from the positions of millions of galaxies. Then they take a deep map of the residual infrared fluctuations and see if the two align. Do the infrared brightness fluctuations peak exactly where the dark matter filaments are predicted to be? Finding a positive correlation would be a landmark discovery, providing the first direct proof that the cosmic web is not entirely dark. It has a whisper of a glow. It would confirm our models of how the universe is structured on the very largest scales and open a completely new window into the physical conditions within these mysterious intergalactic highways. The quest to find this signature is driving the design of future space observatories. Missions will need enormous mirrors to collect enough light and instruments specifically designed to map the sky at the precise far-infrared wavelengths where this filament emission is predicted to be strongest. It represents the next frontier in cosmic cartography, not just mapping the universe by the points where light blazes, but by the faint connecting lines that give the cosmos its true shape. Success would mean we are no longer just inferring the cosmic web. We would finally be seeing it, reading the story of its creation in its own faint, warm light. Yet every signal captured by our most sensitive instruments travels a long and perilous journey before it can be declared a discovery. It must pass through the intricate optics of a telescope, be converted into digital data by complex detectors, and then survive a gauntlet of processing and analysis. At any point along this chain, an artifact can be introduced, a subtle glitch, a systematic error, or a misinterpretation that creates a false signal, a mirage that perfectly mimics the cosmological phenomenon we are desperately searching for. This is the painstaking, unglamorous work that underpins every claim about the cosmic infrared background, the relentless pursuit of distinguishing a true whisper from the universe's dawn from the countless sighs of our own machinery. Consider the detectors themselves. The sensors on infrared telescopes like Spitzer and Herschel are marvels of engineering, but they are not perfect. They can suffer from transient effects like cosmic ray hits, high-energy particles from deep space that strike the detector and create a sharp, bright spike in the data that looks nothing like a real astrophysical source. These are relatively easy to identify and remove. Far more insidious are subtle instrumental effects like persistence, where a detector that has been exposed to a very bright source continues to see a ghost of that source for hours afterward, creating a faint, lingering signal where none exists. Or consider calibration drifts, where the detector's sensitivity changes minutely over time due to temperature fluctuations or other factors in the harsh environment of space, slowly adding or subtracting a tiny amount of brightness from the entire field of view. These effects can impart a large-scale pattern onto the data that looks astonishingly like the cosmological anisotropies we are trying to measure. Then there are the data processing pipelines, the complex algorithms designed to clean the raw data and convert it into a usable scientific product. Every step in this process subtracting the dark current inherent to the detector, flat fielding to correct for variations in pixel sensitivity, co-adding thousands of individual exposures is a potential source of error. A slight misstep in the statistical weighting of images, an imperfect model of the telescope's point spread function, or a hidden correlation in the noise can all create artificial patterns. Scientists must run countless simulations, injecting fake signals into real data to see if their pipelines can recover them accurately, and then running blank fields through the same process to see if any spurious structure is created from nothing. It is a process of constant self-interrogation, a search for errors within the search for truth. This is why every extraordinary claim in this field is met with intense and often skeptical scrutiny from the wider scientific community. When a research team announces a detection of an anomalous signal in the CIB, perhaps a fluctuation that could be from the first galaxies or even a hint of dark matter, the first question asked is not, what does it mean? But could it be an artifact? Other teams will immediately download the public data and subject it to their own independent analysis, using different software, different statistical methods, and different assumptions for foreground subtraction. They will search for any potential systematic effect that the original team might have overlooked. This process is not antagonistic, it is the very engine of scientific progress. It ensures that only the most robust signals, those that survive every conceivable challenge, become accepted features of our cosmic model. Many tantalizing signals have faded under this scrutiny, revealed to be nothing more than subtle instrumental quirks. But those that endure become stronger, their reality confirmed by the very process of attempted falsification. This meticulous collective effort to eliminate our own blind spots is what allows us to place our trust in the faintest whispers from the edge of time. The journey to decode the cosmic infrared background is far from over. In fact, we are standing on the threshold of a new golden age of discovery, powered by a wave of groundbreaking observatories designed to see the unseen. These aren't just incremental upgrades, they are revolutionary instruments that will transform the faint, blurry whispers we've been straining to hear into a clear, high-definition chorus, revealing the hidden universe in ways we can only begin to imagine. At the forefront of this new era is the James Webb Space Telescope, an engineering marvel that is already rewriting the cosmic history books, but Webb is just the beginning. It will soon be joined by a specialized fleet of missions, each with a unique role to play in unraveling the infrared sky's deepest secrets. Webb's most immediate impact has been its staggering resolution. Where previous telescopes like Spitzer and Herschel saw the cosmic infrared background as an unresolved, grainy fog, Webb's massive mirror and exquisite infrared sensitivity are already piercing that veil. It is performing the critical work of source subtraction in real time, resolving countless faint, distant galaxies that were once mere statistical fluctuations in the background glow. Each time Webb identifies a specific galaxy that contributes to the CIB, it provides a crucial data point, anchoring our models and reducing the uncertainty in what remains. This allows astronomers to refine their fluctuation analysis on the still unresolved light with far greater precision, homing in on the properties of the very first galaxies with unprecedented accuracy. Webb isn't just seeing the obvious, it's providing the context we need to understand the whispers that are left. But to truly map the entirety of this hidden light, we need a different kind of telescope. One designed not for deep, narrow fields, but for painting the entire sky in exquisite infrared detail. This is the mission of SPHEREx, a NASA observatory scheduled to launch in the next few years. While Webb is a powerful microscope focused on specific targets, SPHEREx will be a wide-angle survey camera for the universe. Its revolutionary capability lies in its spectrometer, which will map the entire sky not in a few broad colors, but in 96 distinct infrared wavelengths. Imagine seeing the universe not just in red, green, and blue, but in 96 subtly different shades of color. This hyper-detailed spectral map will be a goldmine for understanding the cosmic infrared background. SPHEREx will use this power to perform a kind of cosmic chemical analysis. Every type of molecule, every temperature of dust emits light with a unique spectral fingerprint. By reading the precise spectrum of the infrared background at every point in the sky, SPHEREx can determine what it's actually made of. Is the excess mid-infrared glow coming from unusual types of warm dust, as one theory suggests? Its spectrum will show the specific signature of those dust grains. Or does that same glow have the clean, sharp spectral feature that would indicate it's coming from the decay or annihilation of a specific type of dark matter particle? SPHEREx is uniquely equipped to search for that exact kind of smoking gun, potentially identifying the nature of 85% of the matter in the universe by studying the most diffuse light there is. It will settle debates about the composition of the early universe's dust and search for the impossible by looking for the spectral ghosts of entirely new physics. Looking further ahead, the European Space Agency's Planck successor mission, currently envisioned as a far-infrared surveyor, aims to tackle the anisotropy problem with overwhelming precision. Its goal will be to map the fluctuations in the cosmic infrared background with such exquisite detail that we can finally distinguish between the various theoretical models for structure formation. It will measure the clumpiness of the background glow down to the smallest angular scales, allowing us to count the true number of those missing dwarf galaxies and determine if they are simply too faint or if our theories of dark matter need a fundamental revision. This mission will also provide the ultimate map of galactic cirrus and zodiacal light, finally nailing down these pesky foregrounds with such certainty that the remaining cosmological signal will be crystal clear. The data from these missions won't work in isolation. They will form a powerful symbiotic network. Webb will identify and characterize individual sources, providing the ground truth for the larger scale patterns. SPHEREx will provide the all-sky spectral context, telling us what those sources and the unresolved background are made of. A future far-infrared observatory will then precisely map the intensity and distribution of that light. By combining these datasets, astronomers will be able to create a three-dimensional, multi-wavelength movie of cosmic evolution, showing not just where the first galaxies were, but how they grew, how they enriched the cosmos with dust, and how their collective energy ionized the universe. They will test whether obscured supermassive black holes truly were the powerhouses of the early cosmos, and if the cosmic web itself has a faint, warm glow. Each mystery we've explored, from population 3 stars to modified gravity, will be subjected to a level of scrutiny that was pure fantasy just a decade ago. We are no longer just listening for whispers from the dark. We are building the amplifiers and translators that will allow those whispers to tell us their entire story. This vast cosmic tapestry we call the universe is woven from more than just one kind of thread. The story isn't told solely in infrared whispers. It's a symphony played across the entire electromagnetic spectrum, from the deep bass notes of radio waves to the piercing treble of gamma rays. And the true magic happens when we learn to listen to how these different parts of the symphony harmonize. The cosmic infrared background doesn't exist in isolation. Its story is deeply intertwined with these other cosmic backgrounds, and by studying their correlations, we can uncover a unified history of how energy was produced, transformed, and distributed across all of time and space. Perhaps the most profound connection is with the granddaddy of all backgrounds, the cosmic microwave background. We've already touched on how their fluctuations are correlated, a handshake between the universe's birth and its first light. But this relationship goes even deeper. The CMB is a pristine record of the universe as it was at one single moment in time, a baby picture. The SIB, in contrast, is an integrated record of everything that happened after that moment, a scrapbook of the universe's entire childhood and adolescence. By comparing the two, we can measure how much the universe was heated and re-ionized after the CMB was released. The energy required to rip electrons away from atoms and heat the intergalactic gas had to come from somewhere, and that somewhere is the very same first stars and galaxies whose combined, dust-shrouded light makes up the infrared background. The CIB is, in a very real sense, the energetic complement to the CMB. It's the record of the energy output that fundamentally altered the state of the universe, whose initial conditions are frozen in the microwave light. Venturing to the other end of the spectrum, we find another fascinating correlation with the elusive cosmic gamma ray background. This is a diffuse glow of the highest energy photons, and a significant portion of it is thought to come from the most violent events in the universe, blazars, which are supermassive black holes shooting jets directly at us, and the aftermath of giant stellar explosions. So what could this possibly have to do with the gentle warmth of the infrared background? The link is through the process of absorption. Those incredibly energetic gamma rays, as they travel across billions of light years, can run into photons of the cosmic infrared background. When a high-energy gamma ray collides with a low-energy infrared photon, it can be annihilated, creating a pair of particles and effectively being removed from the gamma ray signal. This means the intensity and distribution of the infrared background directly shapes the spectrum of the gamma ray background we observe. By studying the gamma rays that do manage to reach us, astronomers can actually use them as a probe to measure the density and thickness of the infrared fog that fills the universe, turning one background into a tool for studying another. Then there's the connection with the more recently mapped cosmic X-ray background. For a long time, this pervasive glow was a mystery in its own right, until it was largely resolved into the combined light of millions of active galactic nuclei. But the correlation with the infrared background tells a more nuanced story. Many of those X-ray producing black holes are the same obscured AGN we believe are major contributors to the CIB. The X-rays come from their incredibly hot inner accretion disks, while the infrared is the reprocessed glow from their dusty outer tori. So a single object can contribute to both backgrounds simultaneously. By cross-matching catalogs of X-ray sources with infrared maps, scientists can identify these hidden monsters and determine what fraction of the total cosmic energy budget comes from black hole accretion versus starlight. It helps us answer the fundamental question: is the history of the universe written more by the fire of stars or the fury of black holes? Even the low-frequency cosmic radio background may hold a connection. A portion of this radio light is thought to come from the synchrotron radiation emitted by electrons spiraling at near-light speed around magnetic fields, often associated with the lobes of radio galaxies or supernova remnants. The star formation that creates those supernova also produces the dust that generates the infrared background. Therefore, in a general sense, the radio and infrared backgrounds should trace the same overall history of stellar birth and death, just recorded in two completely different physical languages. A strong correlation between the large-scale structure in the radio and infrared maps would be a powerful confirmation that we are seeing the same cosmic story told through different chapters, one written in the fury of relativistic electrons, the other in the gentle warmth of interstellar dust. These cross-correlations transform the study of cosmic backgrounds from a collection of isolated puzzles into a unified field of precision cosmology. It's no longer about just understanding one signal. It's about understanding how they all fit together into a single, coherent narrative. Discrepancies in these correlations become the most exciting things of all, as they could point to missing ingredients, perhaps populations of objects that emit in one part of the spectrum but not another, or new physical processes that transfer energy between different forms. By listening to the entire cosmic symphony at once, we move closer to comprehending the full, interconnected history of energy in the universe, from the first spark of a star to the final whisper of a black hole. Looking beyond the planned missions on the horizon, we find ourselves dreaming of even more powerful tools that could finally resolve the whispers of the cosmic infrared background into a clear and undeniable chorus. Imagine an observatory not just in space but on the moon. The far side of our lunar companion offers a permanent, profound silence, shielded forever from the radio chatter and light pollution of Earth. A telescope placed there in the ultimate quiet could achieve sensitivities we can barely conceive of today. Without the distorting veil of our atmosphere and freed from the heat emission of a spacecraft's own electronics, a lunar infrared observatory could map the sky with a clarity that would make even the James Webb Space Telescope seem like a first glimpse. This stable, cryogenic environment would allow for months-long exposures, gathering the faintest photons from the dawn of time without interference, potentially allowing us to directly image the very first proto-galaxies as they flickered into existence. The next leap might come from a new generation of space telescopes with truly colossal mirrors. We are already developing the technology for in-space assembly and manufacturing. Imagine a telescope with a primary mirror not 6.5 meters across like Webb's, but 50 or even 100 meters wide, a vast segmented eye staring into the depths. Such an instrument would have the light-gathering power and resolution to not just detect the sources of the infrared background, but to dissect them. We could study the internal structure of those first dusty galaxies, map the distribution of their star-forming regions, and directly observe the vast torrent of dust and gas feeding their central black holes. This wouldn't just be about counting sources, it would be about writing their detailed biographies, understanding their life cycles from birth to death with a precision we currently reserve for nearby galaxies. With this unimaginable power, we could transition from inference to direct observation in the hunt for our cosmic ancestors. The quest for population 3 stars would move from a statistical analysis of background fluctuations to a targeted search. A telescope of this scale might be capable of spotting the brief, brilliant flash of a pair instability supernova at the very edge of the observable universe, the telltale sign of a first-generation star ending its life. We could watch these events in real time, studying their light curves to confirm their incredible masses and directly measure the volume of heavy elements they blasted into the void, finally closing the book on the dust production timeline mystery. Perhaps the most profound discovery waiting in the faint infrared glow is a definitive answer to the dark matter question. Future ultra-sensitive spectrometers, like those envisioned for missions after SPHEREx, could scan the entire infrared sky with enough spectral resolution to identify a specific, sharp emission line that has no conceivable astrophysical source. Such a line could be the literal smoking gun, the specific wavelength of light produced by the annihilation or decay of a particular dark matter particle. Finding it would not only solve the 85% mystery of the universe's matter content, but would also open an entirely new field of astronomy, dark matter physics. We could then map the distribution of this invisible substance not by its gravity, but by its own faint light, tracing the true architecture of the cosmic web in a way that would revolutionize our understanding of cosmic structure. Ultimately, the faint, all-pervading glow of the cosmic infrared background is more than a puzzle. It is a permanent cosmic archive. It is the universe's own detailed ledger, recording every star ever born, every black hole that ever fed, and every particle interaction that ever occurred across 13.8 billion years. The light from events long since over, from galaxies that have merged and faded, from stars that died before our planet even formed, is still traveling, still contributing to this soft background hum that bathes us from all directions. Resolving its mysteries is the key to reading that ledger in full. The answers we find will not just tell us where we came from, they will illuminate the physical laws that govern all of reality, potentially revealing new particles, new forces, and new chapters in the story of the cosmos that we have not yet even dreamed of. So as we reach the end of our journey through these 25 enigmas, it's worth pausing to reflect on what this faint, all-pervading infrared glow truly represents. It is not merely a scientific curiosity or a technical obstacle for astronomers. It is a living archive, a permanent record of the universe's entire history of creation. Every photon in that background glow is a messenger carrying a story from a specific time and place across the cosmos. Together, they form a collective narrative that holds the answers to the most profound questions we can ask. Where did we come from? How did the first sparks of light pierce the primordial darkness? What is the true, invisible architecture upon which the cosmos is built? And what is the mysterious dark matter that binds it all together? This isn't just a frontier of astronomy, it is a frontier of human knowledge itself. For centuries, we have studied the universe by the light we can see, building our understanding on the visible glow of stars. But the cosmic infrared background teaches us a humbling and exhilarating lesson. The history of the universe is not written solely in brilliant points of light. It is also written in the gentle, persistent warmth of the hidden and the obscured. The most transformative chapters of cosmic history, the birth of the first stars, the furious growth of the first galaxies, the awakening of the first black holes, occurred behind thick curtains of dust. Their brilliant visible light was absorbed and transformed into this infrared echo, a whisper we are only now learning how to hear. To understand our origins, we must learn to read this hidden text. The pursuit of these answers is one of the most thrilling detective stories in all of science, and we are all witnesses to its most crucial chapter. The tools to finally decode this cosmic cipher are either already in operation or on the near horizon. The James Webb Space Telescope is right now peering into the dusty nurseries of the earliest galaxies. The forthcoming SPHEREx mission will soon map the entire sky in incredible spectroscopic detail, reading the color of the infrared background to determine its very composition. And even more ambitious observatories are being planned, designed to measure the faint fluctuations in this glow with precision we can scarcely imagine. Each new dataset will be another piece of the puzzle falling into place. Your adventure into the hidden universe doesn't have to end here. This story is unfolding in real time with new discoveries announced monthly. You can follow the blogs of NASA and the European Space Agency. You can read the press releases from major observatories, and you can watch the presentations from scientists on the front lines of this research. The next decade promises to be a golden age of discovery, a period where the mysteries we've explored today will be transformed into the established science of tomorrow. We stand on the brink of revelations that will rewrite our textbooks and fundamentally alter our understanding of our place in the cosmos. This faint infrared whisper has waited 13.8 billion years to be understood. We are the first generation with the technology and the ingenuity